Hi everybody, my name is Alejandra and I'm a PhD candidate of Delft University of Technology, and I investigate how to optimize mangrove restoration using bamboo structures. And for those who aren't very familiarized with mangrove ecosystems, here you can see a satellite picture of a mangrove forest, which consists of several tree species that grow in intertidal areas, which means that they are submerged part of the day and emerge the rest of the time. Mangroves attenuate waves and currents, so as the incoming flow entering the forest slows down, the sediment particles that are carried in the water column can deposit between the trees. This can be a powerful mechanism to counteract sea level rise, and this is why it is often said that mangroves trap sediment. In the next slide, you can see the picture of a coastline that used to be covered by mangroves. Particularly, this is a picture of Demak, North Java, Indonesia, which is the study site of a research project. And what happened here is that the coastline was deforested in order to build shrimp ponds for aquaculture. And also in the south, there's the city of Semarang, where groundwater extraction has resulted in subsidence rates of up to 16 centimeters per year. The subsidence problems, combined with the loss of vegetation, resulted in coastline retreat. If we take the situation of 1984 as the reference, we can see that in 2000 there's a lot of flooding in the south part of the coastline, and that in 2016 there's pretty much coastline retreat everywhere, with a maximum distance of retreat of 5 kilometers at some locations. So basically we have a situation where the coastline is continuously retreating, which has resulted in areas that are now permanently flooded on the seaside, but also on the land side due to the subsidence. These areas cannot be colonized by mangroves because they are now subtidal. And another effect of these landward locations being flooded is that they have to be filled and emptied by the tide every tidal cycle, so the current patterns in the area have experienced lots of changes. Bamboo structures have been built to mitigate coastline retreat. They're built usually parallel to the coastline or with a small angle with respect to it, and they're formed by bamboo poles. The structures attenuate waves. The smaller waves behind the structures favor sediment deposition, which results in an increase of the bed level and the creation of new habitat for mangroves. The idea is that these structures are temporary, so after a few years the vegetation is restored and it will keep the coastline stable. Although the structures are designed to attenuate waves, they also influence local currents and the sediment transport. Predicting how the structures will influence the flow requires parameterizing the resistance exerted by the structures. So basically being able to predict the forces acting on the bamboo poles depending on how they are placed and the incoming flow velocities. And this is the focus of this presentation. We aim to develop a model that can be used to predict the forces acting on the bamboo poles, schematized as cylinders, and later on this model can be applied in larger scale flow models to predict the spatial flow patterns that will develop around the structures. The starting point of this model is the situation with one single cylinder, where an incoming flow experiences energy losses along the surface of a cylinder, which results in the formation of a wake where the velocities are lower. This difference in velocity causes a drag force acting on the cylinder, which is parameterized as a function of an empirical drag coefficient and a velocity representative of the drag forces. For a single cylinder in turbulent flow, this drag coefficient has a value of around 1. And the flow velocities can be determined, for instance, from the bulk velocities. For open channel flow, this could be calculated from the flow discharge and the cross-sectional flow area. However, for multiple cylinders, this is more complicated because the presence of the cylinders is going to affect the local flow between the elements. First of all, there's going to be a volumetric flow obstruction, so the same discharge has to flow through a smaller volume, and this results in an increase of the average pore velocities. This is often represented using the volumetric porosity. And secondly, recent studies suggest that the velocities driving the forces are better estimated by doing mass conservation in a cross-section rather than in the whole volume. This provides a blockage factor that increases the velocity to account for this. This blockage factor is going to depend on the lateral spacing between the elements. If a group of cylinders is very sparsely placed, there may be the situation where they do not really interact with each other or affect the surrounding flow, so you can assume them as single cylinders. But if the lateral spacing becomes smaller, there will be more flow acceleration and larger forces acting on the elements. Inversely, there can be the situation where the downstream separation between the elements is so small that downstream elements are submerged in the wake of upstream elements, which reduces the velocities and the forces acting on them. And there can also be a hybrid situation where there's both flow acceleration and sheltering. We model these effects by multiplying the incoming flow velocity, for instance the bulk velocity, for open channel flow by two factors, a sheltering factor and a blockage factor. And this parameterization of the velocity can be introduced in the expression of the drag force. Several authors in the literature have determined the drag coefficient by relating the measure of forces to the incoming flow velocities. By doing this, they calculated the bulk drag coefficient, which is a fitting factor that basically incorporates the effect of blockage and sheltering. And the nice thing about using these two factors is that we can relate the bulk drag coefficient to the drag coefficient of a single cylinder and to see how much blockage effects and sheltering effects affected the value of the bulk drag coefficient. By knowing the bulk drag coefficient, we can determine the drag forces acting on an element. In our model, the blockage factor was determined from mass conservation through a cross-section of the array, and the sheltering factor, defined as a ratio between the velocity in the wake to the incoming flow velocity, was estimated using the wake flow model of Imse et al. 2011. Imse et al. Developed a wake flow model for a single cylinder in a current with high levels of ambient turbulence. And this is an important factor because inside a cylinder array, since the individual elements are going to be producing turbulence, this is also going to be the case. In his expression, he predicts the velocity deficit in the wake as a function of the drag coefficient, the cylinder diameter, the downstream distance from the upstream element, and the turbulent intensity. And we use this model to predict the velocity reduction on downstream elements at a distance Sx. We did some adaptations to this expression, as you can see in this slide. You can see that there's a 1 minus in this expression. This is because Imse et al. Calculated the velocity deficit, whereas we're interested in the velocity in the wake compared to the incoming flow velocity, but the rest of the expression looks quite similar. We replace the drag coefficient by the bulk drag coefficient and the downstream distance by the downstream separation between cylinders. And we also included a factor that changes the wake flow model for low Reynolds numbers because in laminar flow the equations change. As you can see from this expression, predicting the sheltering factor depends on knowing the ambient turbulent intensity, in this case the turbulence production by the cylinder array. We determined this by doing a balance between turbulence production and dissipation as done by Neff 1999, where we considered two sources of turbulence production. One of them was production at the wake, estimated as the work done by the drag force, and the second term was due to flow expansion. So basically there's a reduction from the mean kinetic energy as the flow expands, which is transformed into turbulent kinetic energy. And lastly, the dissipation was determined as a function of the turbulent kinetic energy and a turbulent length scale that we chose equal to the cylinder diameter, but it was limited to a minimum value equal to the spacing between elements. By combining these expressions, we obtain an equation that allows to calculate the turbulence production. So for instance, if we have a certain structure with a spacing between cylinders in the downstream and lateral direction, a certain frontal area per unit volume, cylinder diameter, incoming flow velocity, we can introduce these parameters in this equation, calculate the turbulence production, use the turbulent intensity to determine the sheltering factor, calculate the blockage factor based on the geometry, and combine these factors to determine the bulk drag coefficient. It is important to point out that during the model development, we assume all the time that we were working with emergent cylinders because of the structures that were built in Indonesia. The model does not calculate the surrounding flow field, so it doesn't reproduce backwater effects or the changes in the flow depth in between the elements. This model basically estimates the bulk drag coefficient, and the equations can be implemented in a large-scale flow model that could solve for those processes. It might be necessary to discretize the structure in some applications, for instance, if there's a heterogeneous external flow field, or if the structure itself in a particular application causes pronounced changes in the water depth, then it may be necessary to divide the structure in different parts. And as you can see from our diagrams, we mostly focus on regular arrangements, but in the next section we're going to discuss the validation of the model also for staggered and random arrangements. For the model validation, we use the data collected by the master student William Jansen in his internship in Viteben and Bos. Essentially, he considered several configurations of cylinders, one single cylinder, one single row with different lateral spacings, and multiple rows where the elements were placed in different ways. He placed the frame with the cylinders in the middle of a flume, and he measured forces and velocities. So this information was used to determine the bulk drag coefficients. Besides his data, we also used the data collected for random cylinder arrangements by Tinoco and Cowen and Danino and Neff. And here you have an overview table with all the data that we used, including the spacing between elements, cylinder diameter, porosity, flow velocity, and bulk drag coefficient. And to validate the model, we consider three situations. First, we assume that the velocity inside of the structure can be estimated from the pore velocities. So if we introduce the pore velocity in the expression for the drag force, and we express the drag force as a function of the incoming flow velocity and a bulk drag coefficient, now this bulk drag coefficient relates to the volumetric porosity. And this approach resulted in an underestimation of the measured bulk drag coefficients. Secondly, we assumed that the drag forces could be fully described by the velocities due to blockage and that sheltering effects were completely negligible, so the sheltering factor was set to 1. By doing this, we obtained a better representation of the results of random arrangements, but there was a tendency to overpredict the bulk drag coefficient. For regular arrangements that had the same frontal area but different downstream separations between cylinders, this is a process that we cannot reproduce with this model, and there was a big mismatch between predictions and measurements. And thirdly, we assume that the drag forces could be characterized using the blockage factor, but also the sheltering factor, and we explained how to calculate it in the previous slides. This is the method that provided the best match between predictions and measurements, particularly for the regular arrangements. This model could be implemented in larger scale flow models to investigate the influence of the structure setup on erosion mitigation. Another point for future research is how this bulk drag coefficient changes under waves, because this is an essential parameter to predict wave dissipation by the structures and to calculate their effect on the morphodynamics. Thanks a lot for your attention. If you have any questions, you can always ask me during the session, but if there's some other things that you want to discuss, if you have specific questions, you can also send me an email.